All right, week 4, here we are. Welcome to the party, ladies and gentlemen. 5-7 and 5-8 are on deck for today. Well, the good news is there's a lot of crap in 5-7 and 5-8 that I don't care about. So we're kind of going to fast track it a little bit. 5-7 in particular, I'm not... If and when we do have a test on this material, and we take home test on all those lines, I'm not going to do a lot with the ambiguous case for the law of sines. I'm going to explain it here real quick, and then on this particular one, the actual worksheet, I only want you to find the number of possible solutions for 5 through 10. I don't want you to hunt them all down. It's a ton of work that I just don't care about. We're also going to cancel out number 11 as the word problem. So if you thought you were getting a head start on this stuff and cranked it all out in 7 hours yesterday, well, bum deal, but that's the way it goes. So the ambiguous case of the law of sines, I think of it as a wrecking ball and a crane. And this might not make a lot of sense at first, but think about our ground here as the bottom side of the triangle. And this angle is here. I'll say we know this angle, and this is the crane, right? And he's got his little crane arm here. He's doing his thing. Sweet. And we know this length, right? We know this angle, and we know the length of the arm. It's not changing. Check. And then we have the wrecking ball here that hangs down. There we go. And we'll call this, I don't know, B for ball. There you go. So depending upon the length of the chain on the ball, there might be 1, 0, or 2 possible triangles that can come out of this. This might be ringing some early geometry bells when we're talking about side, angle, side, and angle, side, angle, and angle, angle, side, as ways to show that triangles are congruent. And that's synonymous with saying ways to show that only one triangle exists. And you probably recall hearing that angle, side, side was one that does not work and shouldn't be used. And in general, that's correct. If there's more than one triangle that can exist with a given set of criteria, that means you can't solve for all the unknowns because you don't know which one it is. So the thing is, in geometry, this is mostly true, but there's a little bit more nuance to it. By the way, side, side, side was one of the others that can be used. I forgot to mention that. But this is an angle, side, side setup. Angle, side, side. And the answer to this is case 1. You got a triangle, and the chain is just too short. If this happens, you have 0 triangles possible. The problem is not solvable. Done. That's it. Okay. Option 2. Draw this out here, hopefully. It is exactly right here. All right, it's exactly 90 degrees. It's the perfect length. It just barely hits the ground, and that's it. Okay. Case 3, the chain is too long. In this case, the chain could swing in either direction, and there are 2 triangles possible. Extend these out there on the ground. It could be here and an obtuse triangle, and it could be here at an acute angle. So there are 2 possible triangles. Okay. There's one more kind of weird case that's a bonus where I'm going to draw this. There's only one possible, but the chain is so long that by the time that it swings back here, it kind of misses the back end of the triangle. So this isn't really a triangle because we know this angle is fixed, this point in space is fixed. So this isn't really a triangle here. So this one also has only one triangle. So that's the moral of the story. There are these cases that you kind of got to think about if you were trying to actually solve one of these. And you're noticing that they all depend upon how long the chain is in relation to the height of this arm above the ground. So in order to figure this out and break it into a little bit more rigorous cases, you'll notice on the worksheet they give you this table up here. That's what this is doing. This B sine A thing shows up multiple times, and we'll kind of break this down a little bit. So if I have my arm here, and this is angle A, I gotta make sure I'm doing this right, and this is little b, and our question mark crane arm here, our ball and swing thing, is little a, because it's the opposite of big A angle. What matters is how, I label my crap in the wrong damn directions? No, I got it. Yeah, we're good. Is how A relates to this height. We're going to call it H. So the first thing to do is solve for H. And H is the opposite. B is the hypotenuse. That implies a sine relationship. So we can say that the sine of A is equal to H over B. And therefore H times both sides by B is B sine of A. Okay, cool. So that's where this table comes from in the worksheet of saying, well, whether A is bigger or smaller or the exact same length as H depends upon how many triangles you have. Or controls determines how many triangles you're going to have. So if you want to know that, you're going to set it up. And if there are two triangles, you got to play both sides. You got to say, well, they're symmetric, so this angle is going to be half here, and you can build two triangles and you can solve them all. But I really don't want to put you through solving like for 12 flippin' unknown variables on this, because it's overkill. We just don't care that much. Nope. So, got your table here, and you say, okay, if A is less than H, aka less than B sine A, then you got no triangles. 0. If A is exactly equal to H, you got 1. If A is, how do we say this? If A is greater than, is it greater than equal to? I think that's bullcrap. If it's equal to, there's no flipping triangles. It's just a damn line. That's stupid. Yeah, if A is greater than H and A is less than B, then there's two triangles. And lastly, if A is greater than B, and there's one triangle because it's too long altogether. So that's the moral of the story on ambiguous case of law of science. You can dig more into it and it's fine. You can build your cases and it's possible to hunt down which triangle is which and what the heck's going on. But it's not enough of a major issue for me to pick a fight over it right now. Next, we have 5.8, the law of cosines. The law of cosines itself is pretty straightforward. You plug the stuff in, you solve, done. You use it generally when you don't have an opposite pair. You like it when you have, two sides and the included angle. It's useful for that. It also solves side-side setups. We'll give you a little handy problem there for a second. The thing I want to highlight here, kind of out of left field, they pull out this, check out Hero's formula. It's true, it's cool, I guess. But again, I don't care all that much. Hero's formula is one of those things where if you need it, you'll look it up. Like, it's good to know it exists. Yes, you can find the area from three sides. It's possible. It's just a cumbersome, ugly calculation. So here's just practice using it. It says, hey, are you capable of doing it? There's no trig even flipping involved here. That's a little silly. So that's what that is. Bonus points on this one. The smallest angle is always opposite the smallest side, and the largest angle is always opposite the largest side. So there's kind of the sneaky tricksy on that one. The last thing I want to do is look at the criteria for triangle congruence, aka solvability, and break down which ones are solved with which pairing. So side, 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 you do not have an opposite pair. That's a law of cosines problem. Side, angle, side, once again, no opposite pair. That's a cosine problem. Angle, angle, side. Let me think about that. No matter what, you have the angle opposite of one of the sides. That's a sine problem. We'll draw these out in a second. And angle, side, angle. Angle, side, angle. Well, you don't have an opposite pair, so to speak, but there's 180 degrees in a triangle, so you can get one. That's a sines problem. These two you use if you don't have an opposite pair. They get you a pair. And these ones you use if you do have an opposite pair. So what I mean by that, so you have a side, side, side triangle. You don't have an angle and its opposite side that you know. Therefore, this is cosine. Side, angle, side. Side, angle, side. No opposite pair. You can't find the other angles. This is a cosine problem. Law of cosines doesn't require an opposite pair. Law of sine, sine A over little a, sine B over little b. You got to know at least one of the pairs. And then angle, angle, side. Angle, angle, side. You know this opposite pair right here. That's a law of sines problem. And angle. Good. God, that's bad. All right. Angle, side, angle. You don't have the opposite pair, but you know that these two together give you that angle. Therefore, opposite pair. Therefore, law of sines problem. Cool. Pretty fun, ladies and gentlemen. This is the end of this chapter. So, hopefully that adds some enlightenment. Please feel free to email me. And I haven't really had anybody show up for Google Meets. So, I'm doing those, what did I say, noon, Thursday, Tuesday, Thursday, noon. Be there, be square. Cool. Thanks, ladies and gentlemen. Have a fantastic week.